So hi everyone, and welcome to this fourth lecture, as Drew just said. So today we have the pleasure to have Alba Casasbuenas, who will talk about quantitative spectroscopy of massive stars and specifically how to determine surface abundances in those stars. But first of all, let me introduce you the speaker. So she did her master's studies at the Universidad de la Laguna in Tenerife. And then now she is doing her PhD in the same institute, but also in Instituto de Astrofísica de Canarias. And the topic of her PhD is improving the reliability of surface abundance determination in B-type stars. And there will probably be some results soon because she is currently working on her first paper about spectroscopic parameters of B-type stars. So please stay tuned. And yeah, that is all on my side. So Alba, if you are ready, then the floor is yours.
Okay, thank you very much, Sophie, and thank you to the organizers for organizing these lectures. They are being all of them are being very interesting. Okay, so as Sophie already said, my name is Alba Casasbuenas. I'm doing my PhD at the Instituto de Astrofísica de Canarias and the Universidad de La Laguna. And I'm going to be talking about the last lecture in this block of lectures on quantitative spectroscopy of massive stars, which will focus on the surface abundance determinations of massive stars. And this lecture has been very kindly been supervised by Norbert Prisvilla and Miguel Urbaneja. So thank you. So without further ado, I'm going to start. Okay. In this first slide, I am including on the right a spectroscopic HR diagram of massive stars in their different evolutionary stages. And I wanted to say that we're going to, for the purposes of this lecture, we're only going to be focusing on OB stars. Which are these stars over here, and they are divided into different groups. The O-type stars, which are the most massive stars near the main sequence. We have the B-type supergiants, which are the direct evolution of O-type stars. And we have the B-type dwarfs, which are the less massive stars near the main sequence. These are marked in the spectroscopic HR diagram, kind of like this diagonal, which goes from like around B2, B3 dwarfs, the coldest B-type dwarfs, until B8, B9 supergiants, which are the coldest B9 supergiants. And they constitute a natural spectroscopic group, which is defined by the detection of helium lines and constitute temperatures from between 10,000 Kelvin to around 40,000 Kelvin. So due to their very high temperatures, there are not that many spectral lines in the optical spectra of massive stars. Here on the right, I'm also including some spectra of different stars with different spectral classifications. And on the top, we have an OB star, and we can see that it has significantly lower amount of spectral lines than the other colder stars. It's mainly the main lines in their spectra is hydrogen, helium, and some ionized elements like carbon, nitrogen, and oxygen, and some other metals, especially in the B-type stars, like silicon, magnesium, iron, neon, sulfur, and aluminum. And these are going to be the elements that we can actually calculate the abundances of, which we do following this equation here, which is just the number fraction of atoms of one element with regards to the atoms of hydrogen in the star. Okay. So in order to perform, in order to determine the abundances of these elements in any star, we have to perform the quantitative spectroscopic analysis of the stars, and we do this by comparing the observed spectra with the synthetic spectra that we get from the stellar atmosphere codes. So if you haven't already, I encourage you to go back and watch the first two lectures. The first lecture goes into the spectroscopic observations of massive stars, and the second lecture goes into the stellar atmosphere codes that we use to create the synthetic spectra. And it is by comparing these two that we can start the quantitative spectroscopic analysis. Carlos did a very nice review in lecture 2 of the stellar atmosphere codes, but I wanted to go over them a little bit more also in this lecture, particularly to speak a bit about the atomic data that we need to include in the stellar atmosphere codes in order to perform a good determination of the abundances. So if we go back a little bit and we remember some things about the physics of the stars, we know that the interior of a star is made by a completely ionized plasma in perfect thermodynamic equilibrium, which emits as a black body. And then depending on the mass of the star, we can treat their atmospheres in one way or another. With less massive stars, the photosphere has very high densities and pressures, and the frequent collisions are making the radiation field to be very tightly coupled to the temperature. And therefore, with these stars, we can approximate the stellar atmospheres with local thermodynamic equilibrium, or LTE. However, in the most massive stars, the photosphere has much lower densities and pressures, and the collisions are less frequent. Therefore, the mean free path of the photon is much longer, and the radiation field can no longer it's no longer coupled to the temperature of the gas. Therefore, we can no longer use the LTE approximation, and we have to work in non-local thermodynamic equilibrium, or non-LTE. So if we go over these two approximations a little bit more, when we're doing local thermodynamic equilibrium, which again, it means that the collisional transitions are dominating and the radiation field is coupled to the temperature, we can define the atmosphere of the stars by this more or less by these three equations. The Planck equation, which is the black body radiation equation, which shows how the intensity of light at every wavelength is dependent on the local temperature. We have the Boltzmann excitation equation, which describes the population of each energy state of the ions, also based on the temperature. And we also have the Saha ionization equation, which gives us the ratio of ions versus neutral atoms, also with regards to the temperature. So only by knowing the temperature, we can get an approximation on the physics of the atmosphere. However, for massive stars, which are the stars that are pertinent to this lecture, we can no longer use these approximations with the temperature because we're working in non-local thermodynamic equilibrium, or non-LTE. In this approximation, the radiation is dominating and the radiation field is decoupled from the temperature. And therefore, instead of using the previous equations, we have to use the statistical equation, the statistical equilibrium equations, which means that we need to account for each individual microscopic process that is causing an atom to change from one state to another. So we need to take into account both the radiative rates and the collisional rates, radiative and the collisional transitions. The occupation numbers of each energy state of the atoms are found by solving the rate equations that are balancing all of the transitions. And it is important that we have a self-consistent and simultaneous solution of both the radiative transfer and the statistical equilibrium equations. This was explained a bit more in detail in lecture 2. Here on the right, I included a Grotrian diagram, or an energy diagram of the calcium 1, and just to see to visualize what I talk about when I talk about the energy levels. These are the energy levels of calcium 1 divided into their atomic configuration, and we see here the radiative excitations, so the radiative bound-bound transitions that can happen in between levels of this ion, and these transitions are what are causing the spectral lines, but we also need to take into account the occupation number of each of the energy levels that are affected not only by these radiative bound-bound transitions, but also by the photoionization, so radiative bound-free transitions, and all of the collisional transitions. So how do we include all of this data in our stellar atmosphere codes? We do this by including what we call a model atom. Here I include a very nice definition from a review in Prisvilla 2010 about the model atom, which is defined as a collection of atomic input data that is required for the numerical solution of a non-LTE problem. So the model atom is a mathematical physical approximation to the real quantum mechanical system of an atom and how it interacts with the radiation and other particles in the plasma. Okay, so in practice, what this is that we need to feed into the stellar atmosphere code a set of data of the ions of the atoms that are relevant for our spectrum of our massive stars, and we need to include all of the information that we need to solve the non-LTE equations. So this means the description of the energy levels of the ions, so the statistical weights and ionization potential of all of the levels, and as well as all of the transitions that are relevant to the problem. So we were speaking about before, no? The radiative bound-bound transitions between levels, the radiative bound-free transition, the photoionizations, and the collisional excitations and ionizations that are taking place in the atoms. It's very important to have these model atoms be as accurate as possible. Because of course any shortcomings in the atomic model, in the model atoms that we're including in the stellar atmosphere codes, are going to affect the final accuracy that can be obtained in the modeling. And it's also very important that when we cannot while we cannot make sometimes the perfect model atom that has absolutely no problems, it's very important that we test these model atoms by comparing the observed spectra and the synthetic spectra, and have a very well-defined list of reliable diagnostic lines that we know that the atomic data is reliable on this and that we can use for our abundance determination. So where do we get this atomic data from? Where can we get it from? There are a lot of sources of atomic data. They can be experimental or theoretical. They can be tabulated, and they can be approximated through equations. So there's a lot of options. When one has to construct a model atom, it's important to decide what is the best available data that we have and test it in order to and decide what's the best that can reproduce the observations correctly. And like we said before, when it can't, decide what is the reliable list of diagnostic spectral lines that we can use for our analysis. Here I included some possible sources of atomic data. We have, for example, the NIST, which is mainly experimental data and has information on the energy levels as well as the transitions in radiative transitions in between them. A very similar one is, for example, the atomic line list from the University of Kentucky. And there are other databases with radiative atomic information, for example, the NORAD atomic for say Kurzgesagt line database. I also wanted to highlight, for example, the Iron project or the opacity project, which is a very important Yeah, which is a very comprehensive list, or has a very comprehensive database of atomic of radiative data, theoretical calculated radiative data of the energy levels, the transitions in between them, and tabulated photoionization cross sections for a lot of ions that are relevant for the um, for the massive star abundance determinations. Finally, most of the sources that I've mentioned are radiative data. For collisional data, there are not that many comprehensive lists of databases of collisional data. So a lot of the times we need to either rely on approximations of equations, or we can go into the physics literature, and there are some sometimes there are some tabulated data of this collisional for the collisional transitions of certain ions that we can use in our stellar atmosphere codes. And then, yeah, we just need to test the different data until we can build a good atomic model. Finally, when we have the atomic model, we feed it into the stellar atmosphere code, we run it, and we can get the synthetic spectra. Here I included, for example, a Telasti synthetic spectra and a fast twin synthetic spectra with similar parameters. As well as in the bottom, high resolution observed spectra of a star with similar parameters. And yeah, this is what we're going, these are the data what we're going to use to compare and perform the quantitative spectroscopic analysis. So when before we do the quantitative spectroscopic parameters, we need to first have a good determination of the rotational and the spectroscopic parameters before we start determining the abundances. Again, I encourage you, if you haven't already, to go back and watch lecture 3, which focuses on the determination of stellar and wind parameters of massive stars. In which she did a really nice and comprehensive review on how to determine the parameters. And it's only once we have a good determination of the parameters that we can go on to determine the abundance and the microturbulence. So this is maybe you notice that this is the first time that I'm saying this word, the microturbulence. So I wanted to spend a few minutes discussing a bit more about this parameter and why it's important. The microturbulence was originally described as an ad hoc fit parameter that was introduced to remove systematic trends in which it seemed that the chemical abundance appeared to depend on the strength of the lines that we were using for the analysis. So we determined this value of microturbulence, finding the value that minimizes the dependence of the abundance with the line strength. Because of course, if we're determining the abundance of the chemical abundance of an element in a star, we want it to be the same chemical abundance no matter what lines we're using. Here on the right, I'm including an HR diagram from the review of Markova et al. 2025, in which they included the derived microturbulences for a set of different stars in the HR diagram. And in it, we can see that for the OB stars, which are the stars that we are focused on here, the value of the microturbulence is particularly high, in particular when we focus on the B-type supergiants. So it's very important that when we determine the abundances, in particular in massive stars, we don't ignore this parameter, this microturbulence, and we determine them, both of them, the abundance and the microturbulence, at the same time. Studies nowadays are suggesting that this microturbulence could reflect some physical phenomena. It could be driven by small-scale motions from subsurface convection zones or stellar pulsations. However, for the purposes of this lecture, we're only going to treat the microturbulence as this fitting parameter that will remove systematic trends of the chemical abundance for an element. So now that we know what the microturbulence is, we can go on to discuss how the methodologies to determine these two parameters, the chemical abundances and the microturbulences. So here I just briefly presenting both methods. The first method is the equivalent width method or the curve of growth method, which consists of measuring the equivalent width of each spectral line, which reflects the strength of the line, and finding, like we said before, the value of the microturbulence that predicts a constant value for the abundances of all of the lines. And with it, we can find the chemical abundance that is predicted for each line with fixed parameters and microturbulence. Here on the top right, we show the result of an analysis made with this method, where we can see the predicted oxygen abundance for the different oxygen lines of a star with the equivalent width on the x-axis. The other method that we can use is line profile fitting or spectral synthesis, which consists of finding the best fitting model to the observed spectrum by comparing the observed and theoretical line profiles pixel by pixel. This method treats the abundance and the microturbulence as free parameters in order to obtain the best fitting model. So yeah, what it consists of is just comparing the observed spectrum with a grid of models, and the correct parameters will be the ones of the best fitting model. And here we include an example of an analysis made using line profile fitting of a star and the best fitting model that they found. So now I wanted to go a little bit more in detail on how to use the first both methods. In the beginning, I want to talk about the curve of growth method, which, like I said, consists of first fitting the diagnostic lines of the element that we're interested in finding the abundance to Gaussians, and finding the equivalent width of each Gaussian, which is a direct reflection on the strength of the spectral lines. Here I show an example of the fitting of a certain list of silicon lines of a B-type star. So once we have all of the lines measured, for the set of spectroscopic parameters that we have had to determine previously, we can compare the observed equivalent width of each line with the predicted equivalent width of the models with different values of chemical abundances and microturbulences. Here I show an example for some silicon lines. If we focus, for example, on the first panel, we can see that we have on the y-axis the equivalent width and the abundance on the x-axis, and we have the measured equivalent width of this line in the observed spectra, and we can compare it with the different models with different values of abundance and microturbulence. So using these graphs, this curve of growths, we can see which values of microturbulence and abundance are compatible with the observed equivalent width of the observed spectra. We do this for all of our diagnostic lines, and then once we've done that, we can try to find the value of the microturbulence that predicts a constant value for the abundance of all of the lines. Here we have this example. We have in the top different panels for different values of microturbulence, and we can see for each value of microturbulence, the predicted silicon abundance versus the equivalent width of each line, and we can see how we find the value of the microturbulence. In this case, it's between 7 and 9 that predicts a zero slope for the for the tendency of abundance versus line strength. So in this case, it's around 8.5 kilometers per second. Once we found the value of the microturbulence that predicts a constant abundance, we can go back and see what silicon abundance or what element abundance this value of the microturbulence corresponds for the different spectral lines. With our list of diagnostic lines, we see what is the predicted surface abundance of each diagnostic line, and then we can see calculate the mean surface abundances of all of our diagnostic lines. It's very important. Here's where I want to highlight again how important it is to determine correctly the parameters. If the temperature, for example, if the effective temperature is off, here we will not see the ionization equilibrium, which in this case, the orange lines are the silicon 3 lines, and the green line is the silicon 4, and we can see that all of the diagnostic lines are predicting the same value for the abundance, which means that the ionization equilibrium is being fulfilled with the parameters that we determined before. This was what I showed before was for all the diagnostic lines, but now if we use all of the lines that we determine the parameters for, we can see that different lines predict very different surface abundances. This is because historically there have been a lot of problems for the silicon model atom. And this is where it's, again, I want to highlight how important it is to take into account that any problems in the model, in the atomic models that we're using are going to be reflected in the abundance determination. So it's very important to be aware of them and to determine a reliable list of diagnostic lines. So just as a summary, when we're using of this curve of growth method and the use of equivalent widths, the analysis is very fast with this method because we're only using one number for each line, which reflects the line strength. It's very easy to see the effect of the input atomic data on each of the lines, like we saw before. However, it's associating each stellar parameter with a set of diagnostic lines, which ignores possible degeneracies. And if there are any problems with the previous parameter determination, it's going to affect the abundance determination as well. This method is only possible with slow rotators and with good spectral resolution, because it's really important that to take into account any possible blends in between lines. Here, for example, in the bottom, I'm showing here on the bottom right a line where it's being fitted into a Gaussian, but there is a blend and it's not being taken into account, which can lead to possible to problems in the determination of abundances if not taken into account. And yeah, here on the right, I'm showing another work in which they also use this similar methodology, in this case for the determination of nitrogen abundance in O stars. And we can see how they determined for the microturbulence and the nitrogen abundance. They found the value of the microturbulence that predicted a constant nitrogen abundance, and they calculated the nitrogen abundance of the different lines. But this is not a comprehensive list of works that have done this analysis at all. This analysis has been very widely used. It's a very traditional analysis, and there have been there are a lot of works that have used this analysis. On the other hand, we have the line profile fitting and spectral synthesis, which I think might be a bit easier to understand. Because again, it's just finding the best fitting model to the observed spectrum by comparing the pixel by pixel comparisons of the line profiles of the diagnostic lines. So with this method, the abundance and the microturbulence are free parameters that can be used to obtain the best fitting model. Here I'm including an example from the GBAT code doing an analysis of the same B-type star as before. And we can see how it finds the best fitting model for the observed spectra of a list of diagnostic lines, in this case, hydrogen and helium. And it's finding the minimum chi-square for the different parameters by comparing to the different spectra of the grid. In this case, it does at the same time, finds at the same time the parameters, so temperature, gravity, and the helium and abundance and the microturbulence. With this methodology, we can fit several parameters at once, which lowers influence of degeneracies within the parameter space. And this methodology is also possible to do with fast rotators, and it has less influence of spectral lines blending between each other. However, the analysis is slower because you have to do the pixel by pixel analysis of the line profile with a lot of synthetic spectra in the grid, and it can give some problems if it's not correctly normalized here. Because, well, if it's not correctly normalized, we're comparing if we're comparing the normalization is different for the observed spectra and for the synthetic spectra, the comparison will give some problems. Here I'm including some examples of some works that are using this methodology, but again, this is a very traditional methodology that have been used by a lot in a lot of works. So I'm not presenting a comprehensive list of works that are using this methodology here. And then these are the two main traditional techniques that are used for determining surface abundances, but I wanted to also speak a little bit on some other newer methods that are currently being implemented to improve this the determination of analysis and the quantitative spectroscopic analysis in general in the last few years using some machine learning techniques. Here I'm presenting some works, again, not a comprehensive list of works that are using machine learnings, but some people who are doing some important work with machine learning techniques in quantitative spectroscopic analysis. This is very important because they allow the analysis to be sometimes a bit faster. It has lower computational expense. The parameter degeneracies are quantifiable, and it has a good uncertainty. It can provide good uncertainty estimations. And the most important thing that these methods do is that they provide automation, which is essential for upcoming large-scale spectroscopic surveys. For example, WEAVE and FORMOST, in which we're going to have to perform an analysis of many stars very fast, and we need it to be as automatic as possible. Finally, to end with the methodology part of the lecture, I wanted to also spend some time discussing what can we do when we have a binary spectrum, because all of the methodologies that I've described before are only useful for when we have single spectra, single spectra, with only one star. When we have a binary spectra, there are two methodologies that we can follow. The first one is to do spectral disentangling, which is when we have the binary spectra, when we remove the telluric lines and we have a good coverage of the orbital cycle, and we have the photometric information of the stars, we can separate our binary spectra into two individual spectra that we can then determine the parameters and abundances individually with the methodologies that we've used before. Here, again, I include some works that have been working in these directions, and codes that are able to do this spectral disentangling. Again, not comprehensive, but Yeah, and then here on the right, I include an example, in this case from the unwind code, on how to do this spectral disentangling to get the two individual spectra that we can then use to do the quantitative spectroscopic analysis. And finally, the other method is to do spectral synthesis of the composite spectra and having the synthetic models of the binary spectra and comparing it. Here I include again some works that are working in these directions and are able to perform spectral synthesis of binary systems. And here on the right, I'm including an explanatory figure, in this case from SPAMS, on how to create these composite synthetic spectra, in this case, by taking into account the spectra at each point of the surface of the binary system, and then getting the full spectrum that we can then compare with our original binary observed spectra. Okay, so that was all for the methodology part. So now I wanted to focus a little bit also on not only on how we determine abundances, but why do we determine abundances and what can we do with them? What can we infer from massive stars with them? So just again, it's not going to be a comprehensive list of everything we can do, but just a few examples. For example, when we have carbon, nitrogen, and oxygen abundances, these can be really important diagnostic tools for stellar evolution models. The energy production in massive stars is mainly done through the CNO cycle, and therefore we can predict the nuclear paths that the stars follow with a slope that is defined by the initial CNO abundances, regardless of any other model details. Here I include an example, in this case from Martin's 2024, which shows, for example, the nuclear paths of this is nitrogen over carbon and nitrogen over oxygen of the small Magellanic Cloud and the large Magellanic Cloud, the theoretical predicted lines with also the observed abundances that were derived for these stars. These abundances can also give us some information on the rotational mixing of the stars, in which the materials, when stars that are rotating rapidly, the materials can be mixed from the core into the surface. In this case, also when they are together with the helium abundances. When we are doing in the rotational mixing, the nuclear process material, in this case helium and nitrogen, can be moved from the core of the star into the surface, and we can see high helium and nitrogen abundances in the surface of the stars. However, also when we're doing helium and nitrogen abundances, we found that it can also be a tracer of binary interactions. In this case, including an example from this paper from Martinez Sebastian, in which they found that stars with low nitrogen abundances and high helium abundances are not compatible with these rotational mixing processes and are instead tracers of binary interaction through the mass transfer of helium-rich material from one star into another. Something else that we can infer with abundances is, in particular, when we're studying early unevolved, slowly rotating and single B-type stars, these stars are ideal indicators for local present-day cosmic abundances. And here I'm including this figure from the cosmic abundance standard that was determined by Lieban Prisvilla in 2012. In which they found the local present-day abundances of a sample of B-type stars for all of these elements. And here we can also see what we were talking before, that when we have we can have a really good determination of abundances with good atomic models and reliable list of diagnostic lines, which allows us to really narrow down the scatter of abundances in the stars in this case, yeah. And then finally, I wanted to also include when we're looking further away. So the previous one was in the abundances in the solar neighborhood. When we're also studying abundances of stars, which are also further away, we can find information on, for example, metallicity gradients, which are very important constraints for models of chemical evolution and galaxy formation. And here we can see for example, the metallicity gradients in the Milky Way of some stars from Braganza et al. 2019 of oxygen and silicon. And here on the right, also some metallicity gradients with the galactic disk from the Flora Cunha 2004 of a lot of elements. So that was all for the lecture. I just wanted to remind a bit of what we went over. We went over how we can determine surface chemical abundances of OB stars through the quantitative spectroscopic analysis of their optical spectra by two main methods, the equivalent width method and the line profile fitting method. And we saw why each of them is good in its own way. I want to highlight again that the chemical abundance results that we get are always going to be limited by the accuracy of the non-LTE atomic models, which we use in the stellar atmosphere codes. So it's really important to have good atomic models, and then also really important to define a reliable list of diagnostic lines that we can use. Finally, we went over how accurate surface abundance determinations of massive stars are essential for constraining stellar evolution and galaxy formation models. And finally, I also wanted to highlight again that we did not do a very comprehensive study of everything you can do with this very wide topic. There's a lot of things that are missing. For example, what we can do in the UV analysis when we study all of the lines that appear in the UV. And for example, also the possible analysis of more evolved massive stars in other evolutionary stages. But that was all. I hope you enjoyed the lecture, and thank you.
Thank you very much, Alba. It
Thank you.
was excellent. I really love it. Very comprehensive. Yeah. Do we have questions? A lot of applause. Question in the audience? Don't be shy. Yes, Miriam, please go ahead.
Hi, Alba. Thank you for the nice talk. A quick question, either for you or for Miguel, Norbert, Sergio. Do not feel under pressure for this. Could you say a little bit on how to test the atom models? Because I know this is not easy. And what would we need if we come across a new model atom and we want to test it?
So I think the easiest way to test the different model atoms is, okay, wait. And of course, feel free to jump in and correct me if I'm wrong. But we can create the new model atoms. We can compare what we changed between them, and we can calculate the abundances using the new atomic model. And then, for example, I'm going to say what I know, which is using this curve with the equivalent width method. We would repeat the abundance analysis for the new atomic models with different parameters, and we could see how for example, here we have very different determination of this case of silicon abundance for the different lines. We would hope to see that the scatter becomes smaller. So we would take the different atomic models and check if the scatter, if we're able to make the scatter go lower. I think that's the easiest way to do it, and also knowing again, ideally knowing why it's getting lower and why what did we add to make it go lower. For example, if we look at the HR diagram, maybe this line is the one that is giving us trouble and is getting very different abundances. So maybe if we add more levels here or more transitions here, so doing all these types of tests while knowing where the lines are and what transitions we are considering, and trying to reduce the scatter. The scatter in the abundance determination of the lines. So a lot of the times it's hard, for example, for silicon, that we know that there is a lot of problems, but it's always possible to like reduce it as much as possible, no? The scattering between the abundance determination.
Thank you.
So maybe I can add here that in addition to what Alba has said, that you have to take into account all the details about the different transitions and blah, blah, blah. We have to remember that this is a non-LTE problem. So if we have a transition that is not in the optical, but is in the UV, we have to also consider what is happening in our stellar atmosphere. Transition is happening that we know from previous talk, all the line blanketing effects. So it's quite a difficult problem and really needs careful experiments with different effects that can affect the lines.
Okay. I think the next one was Shukwepuka.
Thanks.
Ooh. Yes, I can hear you.
Great presentation.
Thank you.
I have a basic question. Where you showed the early abundance spectrum, the spectrum, the baseline is from 0 and shows a peak. But for the ionized spectrum, it usually shows a dip, is inverted. It shows dip, and the baselines are not from 0. What is responsible for the difference? I don't understand.
Sorry, in what figure? Sorry.
The first one is slide 27, but yeah.
27, okay.
Slide 27, but
yeah,
you have passed the other one that I have used to compare it. Yeah, like this. Yeah, like this. You see the baseline is from 0.0 and it goes up, showing peaks up, up to 1 point. Yeah. But when you go back in the other spectrum, like double ionized or single ionized oxygen, backwards.
I think this you mean that the y-axis is going from 0 to 1 in this case? I think it's because it's only the normal. It's a histogram of the number of stars. So like the total number of stars would be 1, and then so I think it's only taking into account that. So it's about the number of stars in the sample. It's comparing to the total number of stars in the sample that they used here.
Okay, what of the other one that is inverted?
Which one, sorry?
Yes, maybe go back. I've forgotten this. Like this?
Here or here?
Yeah, yes. Like you see, like the baseline now is 1.1, and everything is like showing like deep.
So I think that the stars would be normalized to 1 normally. The continuum of the star would be at 1, and then this is to show, right? This is a bit upwards to show the two individual spectra of the binary system. So I think it's a visualization choice.
Alba, since I'm
Yes.
the author of that figure, I can tell you
Yes.
that you're completely right. Yeah,
Okay.
it's just spaced by 0.1 up, and the other is 0.1 below. Yeah.
Okay.
Thanks.
Did it answer your questions?
Not clear to me. Is the inversion showing absorption?
I think
You see the
maybe I can interfere. I think what your problem is, I guess these two figures have more or less nothing to do. One is a profile or a sequence, the emergent spectrum normalized, whereas the other is a statistical result, which shows about the distribution of the different abundances among different samples of stars, which in former times was quite broad and nowadays is quite narrow. So of course, the abundances themselves comes from such an analysis, but this is a completely different story. So the results cannot be compared here with respect to the y-axis. So maybe you have misunderstood the two plots.
Yes. Okay. Thanks.
Thank you.
Okay, so I suggest I let you think about it, and then you come back to us afterwards if not clear. So the next question, Jesus.
Hi, Alba. Well, great talk.
Thank you.
I have a practical question. So, how many typically suppose you have a spectrum of the whole, let's say 4,000 to 5,000 astrons, and you have an ion that has many lines. Can you fit like, I don't know, 20 or 30 lines? Do your models allow for that, or are they more restricted?
I think in theory you can. So I mean, if we see and like the as most lines as I think the rule is as most lines as possible. No, the only the problem with I think with massive stars is always that because they're so hot, there's so few lines, and sometimes it's very hard to get an abundance determination with a reliable abundance determination with very few lines. But for example, here in oxygen, there's a lot of lines, and here there's for example, an estimation of the abundances of all of the
Let me put it another way. Suppose I go to the atomic light list and I get an ion, let's say like oxygen 2, and I get your models. How many of those? What fraction of those lines are included in your models? How many of them can you fit usually, or you find commonly that there are many levels in which they are basically not in your models? That's my question.
May I answer that?
Yeah.
Answering directly to your oxygen question, if you look at the recent work, for example, from Patrick Aschenbrenner and Norbert Pritzwille, you can see that for B stars, they are fitting basically every single line that is there. Okay. So simultaneously, which again goes back to the first question about the reliability of the atomic data. When you have a wide range and you can fit all the lines, or your model can reproduce all the lines, that means that, I mean, this gives you confidence that things are okay.
Okay, great. Thanks, Miguel. Well, just as a corollary of this, if I have a student who's been processing, but you've seen the publicity. Thank you, Alba, for doing publicity of On1 or new software. So actually, with that software, we are able to combine multiple spectroscopy, multiple spectra, and we're getting very high signal to noise. If anybody here is interested in doing composition analysis of late O stars with hundreds of lines, well, you can talk to me.
Okay, thank you, Jesus. We had a question from Annabelle.
Hi, thank you for your lecture. This is very clear and provide excellent overview of the topic. I want to ask you, in order to use this equivalent wind method to calculate the chemical abundance, how many spectral lines are typically required for obtain a good estimation? I asking you because in the case of planetary nebula, the star don't permit to see the that lines?
So I think with this method, I think the most lines that we can fit, it's going to be better, and it's going to be a more robust result. However, in my experience, and feel free anyone to jump in and correct me, but for example, for the silicon, I've done a lot of abundance determinations of silicon of B-type stars, and there's a lot of problems with the atomic models, and there are sometimes that, for example, here that we've had to do the analysis with 3 or 4 lines. So it's important to have it's nice to have from lines from 2 ionization stages, if possible, in particular with silicon for the ionization equilibrium for the B-type stars. But what you mainly need is to be able to fit to have a good fitting of the microturbulence. So you need more than 2 lines, so you can have a good and yeah. So it's better to have a few multiplets, so your result is not completely biased by only using one set of one transition. But in theory, you can do it with few lines. In my case, I've done it with this, with 4 lines. But of course, it's always going to be more robust and more reliable if you have a larger amount of lines that can give you a more robust result. That's what I think.
Thank you.
Thank you.
Thank you. Joe, you had raised your hand first, so maybe you can go. Unless Jesus, you raise your hand to.
No,
to
sorry,
add...
I forgot to put it down. I'll do it now. Sorry.
Okay.
Okay.
Then Joe, you can go.
Good, thanks a lot. So at first, let me also give a quick response to the question by Jesus and the answer by Miguel Ubanera. So what Miguel was saying is that in the optical, we can more or less, or at least for simpler stars with not too much mass loss and so on, we can reproduce more or less all lines. That's certainly true, but that's only true because the majority of lines which we are fitting are these so-called light elements, C and O and so on, which have only very few nucleons. When we go to more nucleons, particularly, of course, to iron and to nickel, then the quality and the predictive value of the theoretical models becomes less and less. This you see very easily when you look into the line list, for instance, by Bob Kurutz and others, where they make this discrimination between so-called observed and not observed lines. And what you will see is that there are at least 50%, but maybe even more lines, which are theoretically predicted at a certain wavelength, but which are not found. Paco Narave and myself, we have looked into some of these things and found indeed that that for quite a number of stars, the number of predicted lines of observed lines is much lower than the number of predicted lines. So this is something one has to keep in mind. For instance, it's not clear whether this is now only a problem of slightly erroneous energy levels, which would then give rise to the fact that the lines are located at some other wavelengths, or whether it's a general problem. So this was my comment. So now I have a question to Alba. Thanks a lot, by the way, for this very nice talk. Alba, what I have seen is that you have done a lot of analysis with silicon. But what you said just before is you have not so much looked into the atomic models. I mean, you might have compared different ones, but you have not looked into the details. So because my question was, why is there for particular lines, as shown here, for instance, such a discrepancy with other lines? These are particularly 2 lines from different multiplets. Have you any idea? I mean, this is a very old and long problem. But
it's true. But I don't.
Has anybody once commented on this?
It's true, but it's true that everyone that I've talked about the silicon atomic model, a lot of people have done improvements on it. I know Norbert Prisvilla was working on a new silicon atomic model, and I know, for example, Simon Daflon also reviewed the Telasti atomic model, and I think they managed to reduce a little bit the scatter that they find in this prediction of abundances for the different multiplets, and they are able to at least add a few multiplets to the reliable list of lines. But what I've talked, especially with Simon Daflon, I've been collaborating the last few months, and they found they were able to reduce the scatter for Telasti, but with the Telasti model atom, but they haven't been able to completely get rid of the scatter, and they still have some lines that they know that they cannot trust. So we're not sure. That's part of what I want to carry out in my PhD thesis. That's part of what I'm going to be looking into a little bit more in detail, I hope. But it can be many things, no? It can be maybe getting more reliable collisional data, maybe adding a few more levels. Like I know from this, I compared the atomic model that they were using in Telasti and this one that I'm using, and they had more levels, and so maybe that helps adding improving the number of levels. But I don't know if anyone so far has managed to completely get rid of the scatter of the lines. So yeah.
Okay. So
thank you, Alba.
yeah.
I think maybe Sergio has an answer. Or
Yeah, no,
complementing.
in addition to, so
Yeah.
hopefully, and I'm sure it's a pity that Norbert is not here today, because I'm sure he also has a strong opinion on this. He has been working on atomic models for many years. But in addition to what Alba said, for example, in this case, what is happening is that the lines at the silicon, these are probably silicon 3 lines, if I remember correctly, from these are the 41, 88, 30. So this comes from a multiplet that is very high in energy levels, and it's at the let's say boundary of if you go to the Grothendieck diagram, so it's very affected by a cascade effect from upper levels. So it's not only will be very dependent on the number of levels that you are considering close to the ionization edge, but also at some point maybe how you pack all these levels. So probably this is a boundary effect that is affecting a lot this multiplet, because it's not connected with other transitions, while the usual multiplet that we are using is more connected to the resonant transitions, and there are other effects that are affecting more these levels, while this is not happening in the others. So this is part of what Alba is now doing. And yeah, but it's true that many people have worked on this for many years, and it's still not solved. So we'll see. Maybe it's also a question of the GF values. Yeah, we'll see what happens in the next years.
Thank you, Sergio. Maybe Paco, you have something to add?
Yeah, it wasn't on this line. I mean, this behavior reminds me to one that Sergio had during his thesis with the oxygen 2 lines. He had this kind of dichotomy also. And what worries me is normally, if you have the kind of spectra that Jesus is offering the community to have, where you have such a high signal to noise, you want to go for the very weak lines, because the very weak lines, they don't care about microturbulence. Microturbulence just redistributes normally the flux, but doesn't affect the total equivalent width. So those are very, very reliable. So if you can count on them and you trust these transitions, those could be the ones weighted. Now, to what Sergio says about this is something that we already have with the helium-1 atom, the way we pack the levels as well, up to which principal quantum number, and it's a very old story. But what amazes me is that even if it looks like, even if the atom is not very complete, and if you had a more complete atom with more cascading options, you should have those levels less populated, would mean that it would be the other way around, like that you would expect the abundance to be higher. So I guess there's something else in terms of pumping or whatever not included that is maybe affecting that, or maybe those levels are too split and maybe we're missing some of the collisional coupling that is killing them, because in principle those should be the lines you should be using for, provided you have good signal to noise, for abundances, and forget about the other ones. And that was it.
Thank you.
Thank you, Paco.
Can I add something to that?
Yeah, sure, please.
I don't know. I think Patrick is in the meeting, and maybe he can say something. But I believe collisions, because this is Alba. Is this one of the dwarfs, or is a supergiant?
Yes. No, it's a
Collisions
dwarf.
are playing a lot here, and if you don't have all the collisional coupling, as Paco just said, you will have a lot of problems. If I remember properly, and if Patrick is there, he can confirm, using the atomic data that Norbert is using in his silicon model atom, this problem doesn't show. Both triplets can be reproduced simultaneously. And this is due to the fact that Norbert took a lot of care and include all the electronic collisions that are there. And this plays a role. You could, for example, a test that you could do is take a similar supergiant, so a supergiant that would have similar temperature, and see if you have such a huge difference. If the difference is not there, then I would definitely go, or is smaller, I would definitely go for the collisions missing in the model atom, the relevant collisions.
Yeah, I can add to that.
Having said that, there are the silicon model atom, Norbert silicon model atom still has issues. Silicon is giving a lot of problems, and everything that has been tried so far didn't help at all.
Yes, so to add on that, it's true we don't see as much as a scatter as others do, but there are still some discrepancies. But I think overall the model atom I got from Norbert is really well. So we have some discrepancies, but they're way smaller than we see in other papers.
Excellent. Good news. I don't see any question there, but there is a question in the chat, so maybe I can ask it from Rodrigo. So could you please tell us something about the possibility of an instrumental line broadening effect and how to address it when performing line profile fitting?
Yeah, I think so. When you're doing when you're doing the line profile fitting and you're comparing the observed spectrum with the synthetic spectra, it's very important to also take into account all of the, so when you're comparing, of course, when you're creating the synthetic spectra, there is no broadening in it. So it's important to take into account not only the instrumental broadening, but also for example, the rotational broadening, the vicinai and the macroturbulence, to take it into account to broaden the synthetic spectra, and only then is when you can do this comparison, because otherwise, yes, of course, if one of them is more broadened than the other, and if you're not taking it into account, it will give wrong solutions, I think.
Yeah, I think, Rodrigo, you can correct me if I'm wrong, but I think that the question was a bit more how do you get the instrumental effect broadening? So how do you estimate it?
So, Sophie, if you want, I can actually answer that, because one of the things we've been doing with Unwind precisely is that we have been combining the data from different spectrographs, right, to see what is the difference.
Well, you want to break some news here today?
Okay.
Not
No,
sure.
that wasn't me. Anyway, so what I was saying is that, so I've just been comparing precisely using different spectrographs to analyze the same star. And the point is that if your spectral resolution is, let's say, 30,000 or above, it doesn't really matter. So you can take a 30,000 resolution spectral resolution spectrum of a star and a 60,000, and you're going to see essentially the same thing. And on the other hand, if you look at the ISM, you do see differences because ISM lines can be narrower and you can see the difference. So essentially, if you're above 30,000, don't worry about it too much.
Okay, so I think now it answered Rodrigo's question. I hope so. If not, yes, thanks. Okay, do we have any other questions? Existential question. Last option to ask Alba everything. No? Then I think she had enough questions. So I think we can stop here and we can thank Alba again for this excellent talk.
Thank you.
And we do not meet next week because it was the last lecture.